Hi everyone, today we're going to be going over this A2238, which is a 2020 M1 MacBook Pro that does not turn on after a liquid spill. There's some really important data on this, so we need to get this board to turn on in order to pull the data from it. So as always, the first thing we're going to do is plug in our USB-C amp meter and see what amperage and voltage we take and go from there. Alright, let's go ahead and plug in our USB-C amp meter. And let's see what this does. So it looks like we are going to be getting 5 volts and 0.2 milliamps. Alright, it cycles down and it shuts off. Does it cycle again or does it stay off? Okay, so it is cycling. So this is fairly non-specific. What this could be, this could either be a bad CD3217, that's at the top of the list. We could have a missing voltage to one of our CD3217s. Our ROM could be bad. As far as being in DFU mode or anything like that, we don't usually see cycling like that, so it's going to be a circuit issue. Top contenders is going to be either missing voltage or one of our CD3217s are bad, so let's go ahead and have a look under the microscope and figure out what exactly is going on with this poor little M1 board. So first off, I noticed that this has been ultrasonically cleaned. I do notice a lot of areas of previous liquid damage, where previous liquid was anyway, not necessarily damage. And you can just tell this board has been ultrasonically cleaned. So I'm just looking, I want to look and see if there's anything major in the edges, and I don't see anything. Right there we have some corroded capacitors. Those are going to be on PP bus though, so PP bus, short on PP bus could be our issue, but I kind of don't think so, because usually we'll get 5 volts and 0.0 amps. Carrying on. Alright, these caps also on PP bus, corroded, so there's that. This chip, some minor corrosion, that doesn't look too important though. Here's our CD3217 ROMs, and we definitely have some corrosion around our CD3217s. So this is, yeah, this could be suspect right here. So what we see here is there's areas that it was clean prior, and there's still remnants of corrosion, and there's most likely going to be remnants of corrosion under these chips. Along here, our Wi-Fi area too, this was hit too. These capacitors don't look too happy. Carrying on, our ISL 9240 looks alright. Doesn't look too terrible. Always like to do a rundown of the entire board before we jump into anything, just in case, just so we don't miss any areas. Especially on boards that were ultrasonically clean, because there could be liquid anywhere, we don't know. But it looks like it's confined to these areas. So, given the symptoms, cycling especially, my first suspect is going to be this area right here. So these are our CD3217s and our ROM. Now, oftentimes when these guys get corroded, they're just fine. We just need a little bit of flux and heat and they're good to go. So I'm going to put some flux around here. Now, you may notice the flux is a little bit different. I need to make a dedicated video on this, but Amtech has restored the original NC559 V2 formula, and they've actually just had a revision of the original. So this is even closer to the flux that we've had in 2015. And it works very, very well, and it has that characteristic pine scent that we all like. So we're just going to give this a little flux and heat around these CD3215s. And that's going to take care of any corrosion that's lurking under them. Hopefully our ROM isn't bad. I don't think it would be. There's that. Alright, now all the corrosion on this should have been washed out with that flux, and all the solder joints under the chip should have been reflown. Kind of want to touch up this area with my iron, and just because these solder joints look like they could use a little love. Otherwise, it doesn't look too bad here. It just looks like oxidation, post-ultrasonic oxidation. So, get a little bit more flux here. This is going to be UC'd again, so no worries in making a mess. One note on M1 boards, they have thermal compound under the heat spreader for the CPU, so we try and limit our UC times to 1 minute aside unless it's absolutely necessary. just so we don't degrade the thermal performance of the thermal compound under the heat spreader. I would not really like lifting that unless you really have to, but yeah, I do not want to mess with the integrated heat spreader on the processor. Can't tell if these are not soldered or what. It's hard to see one side, but I think they're overall they're okay. Otherwise, this is not too bad. Alright, so let's go ahead and see if this works. I'm kind of halfway whether or not we're going to see similar results or something different, but let's go ahead and see. And also I want to wipe my mat down before I do anything else because there's a lot of flux everywhere. In 5 volts, 0.23, 0.7, it's going to cycle, I bet. Yep, there we go. Alright, so that's not our issue. So, with liquid damage, we have some visual signs here. We have two capacitors here that look not very healthy. So what I'm going to go ahead and do is open up a board view and schematic for this, and we're going to have a look and see what these two guys right here are for, and we're going to see if those are shorted, because when liquid damage infiltrates a capacitor, it oftentimes will lead to a short to ground. Sometimes this is not always immediate. Sometimes it happens after a couple weeks of use or so. So that's why whenever there's corroded capacitors like this, it's always best to either remove them or replace them if necessary. So we're going to go over here to my display capture, and it looks like these two capacitors right here are on PP3V3S2. Now PP3V3S2 looks like it is derived from, or PP3V3S2 underscore Wi-Fi Bluetooth whatever is derived from PP3V3S2. And I'm going to guess this has some play in our USB-C circuit. Maybe not, unless it branches off. It might be unrelated, but it does power some really important system functions here. So I'm just looking around on the board view, getting a feel of where this goes to see if this could correlate to our problem, and I believe it absolutely could. So this chip right here, that's for keyboard LED. I don't care about that. Carrying on. Yeah, so it looks like it just powers some non-specific system functions, and yeah. But the thing is something like that, if it's shorted to ground, that can absolutely cause an issue there. So we're going to go ahead and measure for a short on that. We can just go ahead and do it right on this current sensing resistor right here. So again, I like to, before I start going through all the power rails, I like to just do a run over and see if we could find out what's wrong before we really start thinking on it. So I see a visual sign, I'm going to solve for the visual sign before I get into more in-depth diagnostics. So, but I also know what to look for too. I mean, if you have like corrosion on, I don't know, your keyboard backlight circuit, you're not going to care about that if you're troubleshooting a no power issue. Alright, so do I have a short? The answer is no, I do not have a short. These look ugly, but they are not the cause of our problem. We do not have a short here. So that is not our issue. So, now we have to figure out why our USB-C circuit is doing what it is doing. So there's many possible causes here. We could have a circuit issue here. We could have a bad CD3217. We could have a resistor that's corroded, or we could have a power rail issue. So I'm going to go ahead and start checking my CD3215 or 17 power rails. I always get those two mixed up. Now, if you're confused on where to find what you need to check, there's a really helpful article I wrote on repair.wiki on this. So I'm going to go ahead and show you guys that real quick. keep in mind this is a work in progress, but there are several CD3217 support S2 rails, okay? So we have 5V-S2, we have 3V3-S2, and we have 1V25-S2. Now all of these are going to be sourced from PP3V8 AON. So before we get any of these, we need to check PP3V8 AON because that is basically our VDD main, or one of our main power rails in the system. So we're going to go ahead and check PP3V8 AON, and I believe it is going to be present, but we are going to check here because if it was missing, I think we would get 0 volts altogether. So I'm just going to go ahead and lift this shield right here because this is where our 3V8 AON MOSFETs sit, and those are where the inductors are that I can measure on. So we're going to go ahead and peel this little shield up. It's unnecessary to put this back on, but we do have our PMICs here, and on this side right here we have our 3V8 AON circuit. You can see it's a little, definitely had some residue under there. I don't know if it's liquid or from ultrasonic, probably just from ultrasonic, but we got to check it. So plugged in. And see if I can catch it before it cycles. And I did not. Alright, looks like I have 2.4 volts. Now 2.4 volts doesn't sound like 3.8 volts to me. So that might be a problem here. Yeah, 2.3 volts, 2.38 volts, that doesn't seem... I always... anytime you have a reading that seems wrong, check on another grounding point. And I checked on another grounding point, and we have 3.8 volts, so it's not this issue. So PP5V-S2 is the next one I want to check on an M1 board. So PP5V-S2 is going to be for our CD3217s, and it should show up somewhere around one of the CD3217 chips. But I'm just going to go ahead and do a quick search on my board view, and it should pop right up. So PP5V-S2, and it shows up on several places. So we're going to go ahead and measure on CX404, which is going to show up. It's actually a no stuff. It's a no stuff, and it sits right around here. So right here, and I have 5.18 volts. That is present. So our next one is, let's see here, so PP3V3S2 UPC. Now the UPC one is actually an LDO produced from one of the CD3217s, I believe. Now that powers other functions within the chip, but if we have an issue with one of our CD3217s, it may not output that voltage, and then it won't work, of course. So PP3V3 S2 underscore UPC. Now that one is going to show up probably around a capacitor around one of our CD3217s, and in this case, no, it does not. It shows up all the way over here on a series of resistors. So we got to hunt for these guys. Looks like they show up right here. So right here on these 3 resistors. Now I'm looking at the board view, so feel free to follow along if you have the board view open for this machine. And right here, and I have 3.3 volts. Cross that out the list. It's not that. Carrying on. PP1V25S2 looks like it's going to come from one of our PMICs. Now, PMIC issues are tricky because with PMIC issues, oftentimes they don't fail. They just have external conditions that make them look like they're dead when they're actually not. So that is one thing that we do have to be aware of when we have a missing voltage from a PMIC. We need to be sure that it's actually a PMIC issue and not something causing the issue externally from the PMIC. So this one is going to show up right on this capacitor on the CD3217 that I'm about to measure, and that is 1.225 volts, and that's close enough. So it's not that. So at this point, we know that we have all of our external voltages present for our CD3217s, but they're still not working. So what I want to go ahead and do is have a closer look at some of these these resistors around this chip. So sometimes damage hides under these resistors that we can't really see. So it was, see, was it these guys or it was these guys right here that looked like they were quite damaged. Yeah, look at that. Look at that pad. That is not a pad anymore. Yeah, that is nothing. That is not viable to carry electricity. So same thing with this one right here. Was this one the same? Yeah, this guy's fine. But this one right here has seen better days. I don't know if that's the cause of our issue, but that's definitely something we need to address. Make that pad pretty again. There we go. Let's go ahead and replace that resistor. Let's figure out what value that is. Let's see. Hopefully not some oddball value. It is a 1 mega ohm resistor in 201 package size. So we will go ahead and grab one of those and replace it. Now, I sincerely doubt this was our issue, but it still needs to be addressed. If I were to bet what our issue is going to be right now, it's going to be one or both of the CD3217s is bad. There's that. All right. So there's, in a rare case, there is something called an active short. It could occur when there's only when there's power applied to something, and these capacitors right here do concern me a little bit for that. So I want to go ahead and get rid of these. I don't want to risk having something left on the board that could possibly fail and be trolling us, so I'm going to go ahead and get rid of these guys. And get rid of this underfill around here a little bit, and then I could just wiggle them off. Keep in mind the M1 boards will not boot without Wi-Fi, so do not mess up the Wi-Fi module in any way. Yep, see, I'm just sticking my X-Acto knife through here, and this is going to come right off. I don't really care about putting these back. They're just decoupling capacitors, so for data recovery we usually don't worry about these, but I may elect to put them back. We'll see. It all depends on risk. So I'm going to use the same way. I'm just applying pressure to that capacitor. And sometimes it'll be stubborn. Sometimes they will be stubborn. But I don't want to use heat around my Wi-Fi IC, because if we use heat around our Wi-Fi IC, we can float it. And again, if the Wi-Fi IC is not present on the board will not boot. So there's that. That's taken care of. Let's see if we have any change in our symptoms. I don't think we will. Not yet anyway. So just plug this in. And let's see here. 5 volts, 0.21, 22.4. And same thing. All right, so it's not that. At this point, we know it's not our support voltages. We know it's not that one resistor. Let me clean this area up a bit. So I'm just going to go ahead and dip this part of the board in the ultrasonic cleaner just to clean it up a bit more and so I could have a better look. And then I'm most likely going to replace both of the CD3217s because at this point in time, it seems like the most likely cause of our problem. I actually don't need to clean it up. I can see good enough from here. Just going to have a better look here. Looks good. Looks okay. That resistor should be touched up. But nothing abnormally bad here. Definitely a fair bit of corrosion. Yeah, so let's just go ahead and touch these two resistors up. We'll test it. It's not going to be this. I'm just telling you from experience. It's not these two resistors. One of the CD3217s is most likely dead. So I'm just going to touch these guys up. Just like that. That one is going to be a little bit hard to get to. This one is fine. There, that one's fine as well. All right, let's go ahead and pull these. Let's note orientation. The dot is in the bottom right corner on both of them. So let's go ahead and take these guys off. Any kind of cycling on a USB-C port raises my suspicion for a bad chip or a ROM issue or ROM communication issue compared to an external circuit issue. They don't look too bad under them. Definitely seen worse. Where'd our other one go? It flew off. Okay, it's right there. Make sure it did not nick anything. Nope, looks good. Let's see. Yeah, these don't look too bad. But again, most of that corrosion would have been washed out anyway, so. There's that. I'm going to go ahead and get two new ones reballed. I'm going to set these aside just in case they are just in case they are good. Could kind of get a better look now that they're off. That's just superficial. Our ROM looks pretty good. Alright, let's clean this area up and prep for some new chips. So what I'm going to do, flux, solder, and clean up this lead-free solder because it makes our job much harder. So we're just going to feed some leaded solder in here, 6337. Clean all this up. Just like that. Let's wick this. Always like wicking these, especially with this weird ball pattern that these guys have. So I don't want my chip to sit kind of funny and then bridge balls under it, so I want it to be totally flat. Just like that. Same thing on this one. And that's good. Let's go ahead and grab two new chips. Alright, let's get our new chips in place. We have plenty of flux down here, so we don't have to worry about adding any more. I'm going to start out with low airflow. Just going to get this close. We do have 138 degree solder here, so it should go into place pretty easy. Make sure it's flown into place. 138 can be a little bit tricky. It could trick you into thinking it's down when it's not. It is definitely down now. Give it a little nudge. It is good to go. Now for our next one. Now we will need a little bit of flux on this side right here. And it looks like we have some debris. Let me get that out of here. I don't want any fibers of Q-tips under my soldering surface. Let's grab our other chip here. And place that down here. Always double, triple check your orientation because you don't want to put a chip on the wrong way and cause a crater under the chip because you soldered it the wrong way and now your board has a massive hole inside of it. So always be cautious of your orientation. And surprisingly, I've been asked many times, does orientation matter? And the answer is yes. It always matters in any kind of IC. Can we save it? Oh, that's risky, but I think it'll be alright. That'll be a miracle if it's alright. Let's see, we gotta tilt it and look at it. That would have been... I think it's alright. No, no way. That would be really something if it's alright. But we're gonna see. So let's let it cool down for a minute. I'm just gonna put it on my air filter right here to cool it down even quicker. But if that works, that would be amazing. That would be one of the most epic saves of a soldering job ever on this channel. Alright, should be cool enough. And hopefully that one doesn't go on fire the second we plug it in, but we'll see here. Alright, so on one port, yeah, one we have nothing. And this one, let's see. 5 volts, 0.22, 0.4. Same symptoms, okay. So yeah, this one I'm pretty sure was the one that we kind of botched here, so let's look at this again. Yeah, it's dead both ways, so it's not that. We'll go ahead and take this off. This one may end up being pretty challenging based on its symptoms, so of course the cycling could just mean we have a bad CD3217 because this one's not soldered, so go ahead and pull this one off and we'll get it reballed. Yeah, I knew that was bad to begin with. There's no way that would have worked, but it was worth a shot. Oh yeah, so it wasn't necessarily bridged. There was just a lot of balls that weren't soldered under it, which is, you know, better than bridged. So let's look at this. Yeah, this looks good. We should be able to just put our stencil on top of this and correct it that way. So I'll grab my stencil and get it aligned here so it looks like it goes this way. Let's make sure our solder balls are hardened before we do this. Looks like they are. Just like that. And we'll put a little bit of solder on here. Or solder paste, I should say. I don't really like using wet paste like this, but we're in a hurry, so not really in a hurry, but I do want to get this done before the end of the day, so We're just going to do that. Do 230 or 265 and do 4% air. We're going to hold the chip like this. We want it to be preheated. That looks pretty good. Of course, the real judge is when we take the stencil off. This guy right here could use a little bit more. So whenever you get a mess like that, you could just get a Q-tip and wipe it up on the stencil. Just like that. And I just want to get a little bit more solder in that one. The rest look pretty decent. I could just swipe over the chip again. Just like this. Again, clean it up. Now we'll move back in with the air. And almost done here. Come on. .138 is a little bit harder to work with compared to 183, but it does the job. And that should be good. We're going to let it cool, then we'll pull this off. So I don't really want to move my tweezers, or I shouldn't say that. I just need to come off this very, very easily and gently. It's like that. We're going to wait for it to harden, and then we're going to remove our stencil. So let's just watch what I mean by harden. Keep an eye on those shiny balls. See that? Still a couple more here. See, the shiny ones are still molten. And you'll just notice they become progressively less shiny. Like some of them will be a little bit shiny, but it shouldn't be like glistening or glycering. And there's our final product. And what I always like to do is give them another little reflow just to wash away the excess solder balls right there. Just like that. And that looks pretty good. Again, don't touch the chip until the solder balls are hardened. Go ahead and watch that chip and you'll see what I mean. You'll see them harden one by one. So we'll go ahead and clean our board off, and hopefully our next go will go a little bit better than this one. So I'm going to go ahead and do the same thing. We're going to clean this up. Come on, heat up. There we go. Time for wick. Good to go. Let's clean out this excess flux. There's that. We're going to get a little bit more down here. And let's grab our chip again. And this time we're going to be even more careful to make sure we're in the right position on it, because if it's just off a little bit, you will have problems. I'm going to kind of hold the chip this time. While using my other one as a reference. There we go. It's down at least on some balls. We're going to heat. And there, that should be good. So let's just let it cool and then we'll test it and see if it works. Alright, so we actually have the same exact behavior compared to prior to the CD3217 replacement. So now I'm thinking something more systemic is going on. And when I think about that, especially in an M1 board, I want to break out the thermal, because this is something that could be a million different things, and I want to see if thermal imaging can give us any hint to what might be cycling or what might be going on and why the board is shutting off. So I'm going to go ahead and get out the thermal camera, and we're going to go ahead and have a look at the board and see if we could see anything abnormal around any of the PMICs, maybe even around the processor, anything like that that might be causing this weird cycling-like behavior. Okay, so in M1 boards and thermal imaging, I like to look around our PMICs. So we have one PMIC right here, and we have another one under the shield over here. So let's go ahead and get this in focus, because this does not look like it is in focus very well. There we go. Our other one is right under here, and I always like to look at these guys to see what they do, because oftentimes shorts on these boards will be on a subrail that these guys power. So what you'll see is you'll see a part of the chip get hot, and you'll see one of the inductors get hot next to it. So let's go ahead and see if we see anything. So we're turning it on. Anything? Nothing? Nothing at all on that one. It's totally cold. What about on this one? Alright, I see a little bit of enhancement of that one coil on the top. Yep, definitely see that. So look at that. Let's zoom in so you guys can see what I'm talking about. Alright, so see this? What do you see? You see two inductors that are primarily hotter than the other ones. That was just glare right there when I moved it. But look at that. You see the chip get hot, and you see these two inductors on the end a bit warmer than the rest. See that? So something is powering on that's causing current to be drawn, that's causing load to be put on that chip, and hence those coils are heating up. So let's go ahead and look at that. What is this line? So let's see here. PPVDD SoC S1. So that's processor power. And PPVDD eCPU awake. Alright, so if the CPU is turning on partially, that can be normal. Okay, so that is maybe abnormal, maybe normal, we don't know yet. Carrying on, we've noted that, and we're going to carry on. So we know that is potentially a problem. We have it noted mentally. Now we're going to carry on. Oh, wonder what this might be right here. That looks like that stands out really well. What could that be? I don't know, but that just stands out to me as being abnormal on any board. When it's cycling, when you see a component just light up like that, that does not look right. Especially the way it's very in tune to its cycling. As soon as the USB-C amp meter shuts off, this gets cooler. Look at that. Yeah, that does not look right. Now I wonder what that might be. So that is right above these 3 caps. Looks like it might be a buck converter of sorts. It's this chip right here. Is it this one? How many caps are above it? And that's actually for our keyboard backlight. I remember when earlier we were talking about in the video, I said I wouldn't care about keyboard backlight if we're having a no power issue, but how ironic. Imagine that. Anyway, let's go ahead and look under the scope at this guy. It's for keyboard backlight, so I should just be able to rip that off and it should turn on if that's the case. Let's see if it looks. See, that doesn't look. Alright, that definitely had liquid hit it. It's a MOSFET of some sort. So the question is the MOSFET bad, or is something that the MOSFET powers bad? But either way, we're just going to get rid of him. We're going to say goodbye because it's corroded anyway. Yeah, keyboard backlight shouldn't even be enabled without the keyboard plugged in, so I should not have this heating up. Here we go, come on. There we are, that's off. Let's let it cool and let's go ahead and plug it in again and see if it does turn on now. And my guess would be maybe, maybe not, you never know. Sometimes when you have thermal enhancement like this, it could lead you down a rabbit hole a little bit, because it could be something on a rail that this MOSFET powers, which would be something to do with keyboard backlight. Anyway, should be cool enough now. Let's go ahead and plug it in. Let's see what we get. As long as my port stops being stubborn and actually plugs in. Let's see. 5 volts, 0.19, that's different. 0.3, 0.2, 0.1, and same behavior. Interesting. Okay. So that tells us nothing. Oh, 20 volts. Alright, here we go, 20 volts. Now, don't get trolled on M1 boards, and this is something that I've been trolled so many times on these guys. You look at this and you say, must not be booting, look at that amp draw. Well, the answer is oftentimes wrong, because I have seen these 20 volts, 0.0 something be fully booted into the operating system. So, on any M1 board that you get 20 volts and it is 0.0 something and you're like, oh, well, it must not be booting. Throw it in the enclosure and test it, because oftentimes you will find that because these new CPUs are so power efficient, I mean, these new processors are very, very power efficient, they will be in weird amp draws like this and be fully booted in the OS. So grab an enclosure, plug it in, and see if it works. We're going to go ahead and do that now. Alright, our board is set back in our enclosure. I just have the screen and the USB-C port plugged in. That's all we really need for now. I just want to see if this boots up. And I'm just going to keep pressure on this port, because there's no screws in it, and there's a bit of flux on it, and flux can cause it to kind of, not make as best contact as it can. We have 20 volts, 0.07, 0.17. That is an Apple logo. Look at that. The screen is destroyed on this, I can tell you that much. The enclosure is in pretty bad shape as well, so honestly, on this machine, we're probably not even going to worry about keyboard backlight. Because this is probably not going to be usable. It probably needs a new keyboard. We'll go ahead and put that MOSFET back anyway. But there's some stuff that is just like, what's the point? Are you going to spend money on a new screen, a new keyboard, new battery? It's just not practical. But the thing is, if we can get to a progress bar, if we can get to an OS login, we can get data. So we're going to just let this boot. Sometimes they can take a minute because the CPU is throttled with everything unplugged that we have here. It's moving along slowly but surely. Come on, little M1, you could do it. I know you can. Alright, graphics switch. That's why it went dim. It's still there. There we go. You probably can't see that because, you guys can't see that because it's all dark. But this is booted into an OS. There, you can see it now. The brightness setting is all the way at the minimum, but this does boot, and we will be able to get data on. So I'm just going to go ahead and replace the keyboard backlight MOSFET. There we go. All right, so there it's brightening up now that the light sensor is kicking on. There we go. Because if I turn it this way, it's away from the light. It thinks we're in a dark environment. But if I turn it this way, it'll brighten up, and it does work. So I'm going to go ahead and replace that MOSFET. Again, I don't think this device is ever going to get used again because of the condition of the screen. It's really hard to say, but we're going to go ahead and replace that MOSFET just to make sure, just in case. But until we've tested fully, I'm going to presume that this has keyboard issues and a bunch of other stuff wrong. So let's go ahead and just replace that MOSFET real quick. But this does work. I just want to show people that I don't leave important stuff off of boards unless it's necessary. But we're going to go ahead and replace that MOSFET. Where was it? Right here. Here we go. All right, so this was, let's look at our board view again. UP900, and this is a keyboard backlight PWM level shifter. So let's go ahead and find UP900 on a 820-2016, which I have a donor of. Sometimes they use the same component numbers, sometimes they don't. I'm just going to give it a shot. And what do you know? It does have the same component on the 820-2016, the M1 MacBook Air board, which is quite convenient and helpful for us. So let's go ahead and just touch this up a bit, get some solder. And then this will go to ultrasonic cleaning again because it is filthy, and get reassembled and the data transferred. Gonna load this area with flux too because could tell that it definitely had liquid here before. This had to have been a lot of water spilled on this machine to get the screen. All the screen's all stained. You know, the bottom, the keyboard is all corroded on the bottom side. Come on, little bridge, get out of here. There we go. All right, what's our orientation here? So on this one would be in the, hang on here. Always double check orientation, please. Got it, okay. And let's pull it off the donor board. So, if you guys recall, I did take 2 capacitors off of our Wi-Fi circuit area. Now, I am not putting those back because we have to use heat for that. It's in really close proximity to do it with an iron, and you're probably going to, you know, fumble with it for a little bit trying to get your iron in there. And I don't want to risk doing any damage to the Wi-Fi IC because, as I said, you do need the Wi-Fi IC to boot and ultimately access data. So those capacitors that we removed are non-critical decoupling capacitors. Basically, those guys just make sure that in the event that there is a little bit of noise, the capacitor absorbs it. Now, let's say if you're really, really lucky one day and those capacitors are removed, and let's say there's a solar flare, what might happen with those removed is you might drop a Wi-Fi connection or something like that. It's not like the board is going to fail. It's nothing critical, and it would be under very specific circumstances because the line feeding it is already a very stabilized line that already has a ton of decoupling capacitors on it. So we don't have to worry about stuff like that, and it is much more risky to replace those 2 capacitors than it is to just leave them off and let them be. So it looks like this guy right here is a little bit corroded too. That's how I know this board was just decimated with water. I mean, this got everywhere. Really wonder what it looked like before ultrasonic. In some cases like this, is you're going to drive yourself crazy chasing every little component like this that's corroded when the ultimate goal is data recovery. Come on, little bridge. Get out of here. You're not wanted. There's that. Now, zoom in on this guy. It's kind of hard to see. I think the chip is fine, but the pad has seen better days. But that just runs over here. So what I could do, this looks like a sensor of some kind, either a current or voltage sensor. So we're going to just run a little wire to this. I need my really thin jumper wire, which just seems to be hiding from me. You always have this one thing that's right at the edge of your desk, and then when you need it, it's never there. It's gone. But here it is here. So let's go ahead and just run a little tiny jumper on this. There's that. Just want to get it down on this other point right here. Now that it's anchored in two spots, I could use my soldering iron and make it a little bit of a better joint. And did that just come off? That did just come off. Nice. Okay. Let's clean it up again. Little jumpers like this can be such a pain. And sometimes your flux gets really burned up and makes it even harder on you. Oh look, we don't even need a jumper now. It just fixed itself. So we got a nice little solder bridge over to that pad. We're good to go. Perfect. Alright, so anything else? I'm just going to scan over it. Yeah, some corroded capacitors here. But again, it's data recovery. Like I said, this enclosure it's pretty bad. I mean, screen, probably keyboard. But at least it boots, and we will be able to get data now. So we're good to go on the board. It is booting. We're going to go ahead and get this ultrasonically clean, then pull data, and that is it. It boots, it turns on. It is good to go for data recovery. So that's it for this one. Thank you for watching, and I hope this video helps you in some way. I'm glad we did cover that diagnostic aspect on M1s. Whenever you have some erratic amp draw readings, thermal imaging is an indispensable tool. So definitely use it. But that's it for this one. Thank you for watching.